Almost everyone is familiar with the Pythagorean theorem, which gives the relationship between the sides of a right triangle. In this video, I'll present two new proofs of the theorem that I hope you will find interesting. The first one is a geometrical proof, and while it's admittedly not a particularly clever proof, I still use the same ideas of similarity and scaling of triangles and so forth. It is still very dear to me since it was my first experience of writing my own proof some 20 years ago when I was in high school. The second one is what I'm kind of more excited about since it implies an outside the box kind of thinking. I'll show that the Pythagorean theorem follows as a necessary consequence of the linear momentum conservation principle of physics, which may surprise some of you since we don't usually see mathematical proofs resting on physical facts. Indeed, it is the other way around. Now, this proof was inspired by Archimedes' method of mechanical theorems, in which Archimedes uses mechanical reasoning, law of the lever to be precise, to prove geometrical propositions. For example, Archimedes finds the area of a parabolic segment using entirely mechanical reasoning, which I've always found quite fascinating. In a similar vein, I'll use the linear momentum conservation principle, as I've said earlier, to prove the Pythagorean theorem. But before that, let's see the geometrical proof of my high school years. We start with a right angle triangle ABC of lengths as shown in the figure. First, let's add some constructions to the figure. Through A, draw AD parallel to BC and equal to AB. Next, join BD. Draw DE parallel to AC and produce BC to E. Finally, join AF such that BF has the same length as the hypotenuse AB. With these constructions in place, we are now in a position to deduce several facts which will help us to prove the sought result. First, consider triangle ABD. Since AB equals AD by construction, angle B equals angle D. This, of course, follows from symmetry. Also, since AD is parallel to BC, which is also by construction, angle ADB equals angle DBE. From these two equations, we get angle ABD equals angle DBE. From the last result and together with the fact that triangle ABF is isosceles with AB equal to BF, we deduce that BM is perpendicular to AF, which follows from the RHS congruency criterion. Therefore, angle BMA equals angle BMF equals 90 degrees. Consider now right triangles AOM and BOC. Angle M equals angle C equals 90 degrees. Also, they share an angle from a pair of vertically opposite angles at O. Therefore, they are similar. Hence, angle OAM equals angle OBC. Finally, we consider triangles ACF and BED. They are both right-angled and from the last result have another equal angle. Therefore, they are similar. The ratio of corresponding sides will be equal. Taking the ratio CF by DE equals AC by BE and plugging in the values for the various lengths, we get, after some simplification, the required result, that is, the Pythagorean theorem. Consider a bomb of mass 3m at rest. Now, due to some internal chemical reactions, the bomb suddenly explodes into three identical masses, each of mass m. Let's assume that two of them, moving with velocities v2 and v3, are moving at right angles. Since the internal action-reaction pairs cannot alter the motion of the bomb as a whole, its center of mass, that is, initial momentum must be equal to the final momentum. Since the bomb was initially at rest, the momenta of the three masses must add to zero. In particular, the components of the momenta of the three masses along any line must add to zero. Let's then take the momentum of the three masses along the line of motion of the mass moving with velocity v1. Adding the components of the momenta of all the three masses and setting that equal to zero gives us our first equation. Similarly, we add the components along the lines of the motion of the other two masses to get two more equations. Now we have three equations in four variables. We can eliminate the v's to get the following identity. This is just Pythagorean theorem in a compact form. In other words, the linear momentum conservation principle demands that the Pythagorean theorem be true.